Venus and Earth, born from the same cosmic dust, shaped by the same star, and forged under similar gravity and chemistry. Yet one is a paradise of life, and the other is a world where metals melt in the rain. How did these twin planets split paths so violently? And is Venus a vision of Earth's future or its forgotten past? Picture this. 4.5 billion years ago, two rocky worlds took shape in the inner solar system. Both had iron hearts, rocky shells, and thick blankets of gas wrapped around them. Both received warmth from the same young sun. Both were cousins in size, weight, and composition. If you were a cosmic observer back then, you might have bet that both worlds would follow similar paths. But you would have been spectacularly wrong. Today, one of these worlds hosts billions of species, liquid oceans, and a gentle atmosphere that cradles life. The other world has become a furnace where lead would flow like water, where the air itself could crush you flat, and where sulfuric acid rains down from poisonous clouds. This is the story of Venus, Earth's twisted sister. A planet that had every opportunity to become a second Earth, but instead became a cautionary tale written in molten rock and toxic skies. Venus didn't fail gradually. It didn't slowly drift toward doom. Instead, somewhere in its ancient history, it crossed a line that sealed its fate forever. What makes this story so haunting is how easily it could have been different. Venus wasn't cursed from birth. It wasn't placed in some obviously hostile part of the solar system. For perhaps billions of years, it might have been a world where you could walk under open skies, where water might have pooled in ancient seas, where the temperature was just right for the chemistry of life to begin. But something went catastrophically wrong, and understanding what happened to Venus might be the key to understanding whether Earth's own paradise is as permanent as we hope, or as fragile as we fear. Let's start where the similarities begin, because they make what follows so much more surprising. When astronomers first turned their telescopes toward Venus centuries ago, they called it Earth's twin. This wasn't just poetic language or wishful thinking. The numbers told an incredible story of similarity that still amazes scientists today. Venus is 95% of Earth's diameter. If you could somehow place them side by side in space, the size difference would be barely noticeable. Venus measures about 12,100 kilometers across, while Earth spans 12,756 kilometers. That's a difference of just 656 kilometers, roughly the distance from New York to Detroit. The mass comparison is equally striking. Venus weighs in at 82% of Earth's mass. In cosmic terms, this makes them practically identical twins. Most planetary siblings in our solar system show dramatic differences. Jupiter outweighs Earth by more than 300 times. Mars weighs only 11% as much as Earth, but Venus and Earth, they're in the same weight class entirely. But the similarities run much deeper than surface measurements. Peer beneath the clouds and atmospheres, and you'll find that both worlds are built from the same fundamental blueprint. Both planets have iron cores, roughly half the diameter of the planet itself. Both have thick rocky mantles, made primarily of silicate minerals. Both have relatively thin crusts compared to their overall size. This wasn't an accident. Venus and Earth formed from the same disk of dust and debris that surrounded our young sun 4.5 billion years ago. They condensed from similar materials at similar temperatures. The same processes that built Earth also built Venus, just 700,000 kilometers closer to the sun. To put that distance in perspective, 700,000 kilometers might sound enormous, but in astronomical terms, it's practically nothing. Light travels that distance in just 2.33 seconds. If Earth's orbit were a running track, Venus would be running in the lane right next to us. This proximity placed Venus at about 7/10 of an astronomical unit from the Sun, while Earth sits at exactly 1 astronomical unit. An astronomical unit is simply the average distance between Earth and the Sun, about 150 million kilometers. So Venus receives about twice as much solar energy as Earth does today. That might seem like a lot, but early in solar system history, when both planets were forming their first atmospheres, the Sun was actually about 30% dimmer than it is now. This means that early Venus, despite being closer to the Sun, might have received solar energy levels surprisingly close to what Earth receives today. Some climate models suggest that if Venus had developed the right atmospheric composition, it could have maintained surface temperatures suitable for liquid water. Both planets started with what scientists call secondary atmospheres. Unlike the gas giants with their thick envelopes of hydrogen and helium captured directly from the solar nebula, terrestrial planets like Earth and Venus had to build their atmospheres from scratch. They did this through a process called outgassing. Picture the early Earth and Venus as worlds in violent turmoil. Massive volcanoes erupted continuously, spewing not just lava, but enormous quantities of gas into space. Comets and asteroids bombarded both planets, delivering additional water and volatile compounds. The impacts themselves were so energetic that they vaporized rock and added to the growing atmospheric envelopes. During this chaotic period, both planets likely had thick atmospheres dominated by carbon dioxide, water vapor, and sulfur compounds. The early Earth's atmosphere might have contained 100 times more carbon dioxide than it does today. Venus likely had even more, given its proximity to the Sun and the intensity of its volcanic activity. Both worlds were hellishly hot during this period. Early Earth's surface temperature might have exceeded 1,200 degrees Celsius due to the combination of impacts, volcanic activity, and a thick greenhouse atmosphere. Venus was probably even hotter. Neither planet could have supported liquid water at the surface during this violent birth phase. But here's where the story gets interesting. As the heavy bombardment period ended and volcanic activity began to calm, both planets faced the same fundamental challenge: what to do with all that carbon dioxide and water vapor in their atmospheres. On Earth, as the planet cooled, water vapor began to condense. The first rains lasted for millions of years, creating the first oceans and dissolving enormous amounts of carbon dioxide from the atmosphere. This CO2 didn't just disappear, it became locked up in carbonate rocks, limestone, and other minerals. Earth's carbon cycle began, with plate tectonics eventually recycling this carbon between rocks, oceans, and atmosphere. Venus should have followed a similar path. It had similar amounts of volcanic outgassing. It likely had similar amounts of water vapor in its early atmosphere. And for perhaps hundreds of millions, or even billions of years it might have. Some of the most sophisticated climate models ever created suggest that early Venus could have been a very different world. If it managed to form even shallow oceans, the slow rotation of Venus might actually have worked in its favor. A day on Venus lasts 243 Earth days. This incredibly slow rotation would have created a very different atmospheric circulation pattern from Earth's. On Earth, our rapid 24-hour rotation creates the familiar pattern of weather systems spinning due to the Coriolis effect. But Venus's slow rotation would have created a more stable atmospheric pattern, possibly with long-lasting cloud cover that could have reflected much of the Sun's energy back to space. This high albedo could have kept the planet cool, despite its closer proximity to the Sun. Computer models suggest that this slow rotation Venus could have maintained global average temperatures between 20 and 50 degrees Celsius for up to 2 billion years. That's warm, but not impossibly hot. Many regions of such a world could have harbored liquid water. Life might have emerged. Venus might have become a tropical paradise where evolution could have followed its own unique path. But something went wrong, catastrophically wrong. The question that haunts planetary scientists is this: did Venus ever actually achieve this potentially habitable state? or was it doomed from the very beginning? The answer to this question has implications far beyond just understanding one planet's history. It affects how we think about every potentially habitable world we've discovered orbiting other stars. Recent research has challenged the optimistic models of early Venus. Some studies suggest that Venus's interior chemistry might have been fundamentally different from Earth's from the very beginning. If Venus formed with a drier mantle, with less water locked up in its rocks, then it might never have been able to support surface oceans, no matter how perfect its climate conditions were. But other evidence points in the opposite direction. Venus today has an isotopic signature that tells a story of massive water loss. The ratio of deuterium to hydrogen in Venus's atmosphere is about 150 times higher than Earth's. Deuterium is heavy hydrogen with an extra neutron in its nucleus. Because it's heavier, deuterium escapes to space much more slowly than regular hydrogen. This elevated deuterium to hydrogen ratio is like a fossil record of ancient water. It suggests that Venus once had vastly more water than it does today. Where did all that water go? It was split apart by solar radiation, and the hydrogen escaped to space, leaving behind the telltale deuterium signature. The amount of water that must have been lost to create today's deuterium ratio is staggering. Some estimates suggest Venus might once have had enough water to cover its surface in an ocean 3 meters deep. Other estimates push that number much higher, suggesting ancient oceans hundreds of meters deep. So we have two competing pictures of early Venus. In one scenario, Venus was born dry and never had a chance to develop oceans. In the other scenario, Venus might have been a water world that lost its oceans in a planetary catastrophe so complete that it left only chemical fingerprints behind. The truth probably lies somewhere between these extremes, and upcoming space missions to Venus may finally give us the data we need to know for sure. But regardless of whether Venus was ever truly habitable, the planet we see today stands as a monument to how quickly and completely a world can transform. Understanding why Venus and Earth, born as cosmic sisters, ended up as alien strangers is one of the most important puzzles in planetary science. Because if we can solve the mystery of Venus, we might finally understand just how special Earth really is, and how careful we need to be to preserve the extraordinary world we call home. But did Venus ever really get a chance to be like Earth? This is perhaps the most haunting question in planetary science. Did Venus, our sister world, ever host oceans under alien skies? Did water once lap against Venusian shores while Earth was still a molten hellscape? The answer could rewrite everything we think we know about habitability in our universe. For decades, this question seemed impossible to answer. Venus today is sealed beneath clouds so thick that no surface features were visible until radar penetrated the veil. The planet's surface is hot enough to melt zinc, lead, and tin. Any water that might have existed has long since vanished. But like detectives examining a crime scene millions of years after the fact, scientists have found clues scattered throughout Venus's atmosphere, locked in its rocks and hidden in its very chemistry. The first breakthrough came from an unexpected source: computer climate models originally designed to understand Earth's future. In 2016, a team led by Michael Way at NASA's Goddard Institute for Space Studies decided to turn these powerful models backward in time, asking a simple question: what if early Venus had started with oceans? The results were stunning. The models showed that if Venus had somehow managed to condense water into surface oceans, it might have remained habitable for an incredibly long time. Not just millions of years, but potentially up to 2 billion years. That's nearly half the age of the solar system. That's longer than complex life has existed on Earth. But how could Venus, sitting 30% closer to the Sun than Earth, possibly maintain liquid water for so long? The answer lies in one of Venus's most distinctive features today: its incredibly slow rotation. Venus spins on its axis once every 243 Earth days. That means a single day on Venus lasts longer than a Venusian year, which takes only 225 Earth days. This bizarre rotation rate, the slowest of any planet in our solar system, might have been Venus's secret weapon for maintaining habitability. On Earth, our rapid 24-hour rotation drives complex weather patterns. Air masses spin into hurricanes, storm systems race across continents, and the Coriolis effect creates the swirling patterns we see in satellite photos. But Venus's sluggish rotation would have created an entirely different atmospheric dynamic. The models suggested that slow-rotating Venus would have developed thick, long-lasting cloud decks that covered the entire planet. These clouds wouldn't have been the sulfuric acid nightmares that exist today. Instead, they would have been water clouds, similar to the clouds on Earth, but much more extensive and persistent. These planetary clouds would have acted like a giant mirror, reflecting most of the sun's energy back to space before it could heat the surface. This is called a high albedo effect. Today's Venus actually has the highest albedo of any planet in our solar system, reflecting about 75% of the sunlight that hits it. Early Venus with water clouds might have been even more reflective. The models showed that this cloud shield could have kept global average temperatures between 20 and 50 degrees Celsius. That's warm by Earth standards, more like a perpetual tropical climate, but certainly cool enough for liquid water to exist. Some regions, particularly at higher latitudes or elevations, might have been quite comfortable by human standards. Imagine walking on this ancient Venus. The day-night cycle would have been almost unimaginably slow. You could watch the sun creep across the sky over the course of months. The thick cloud cover would have created a diffuse, even lighting similar to an overcast day on Earth, but lasting for months at a time. Rivers might have flowed, fed by the slow evaporation and condensation of a global water cycle, operating on geological timescales. But these tantalizing models raised as many questions as they answered. Even if Venus could have maintained habitable conditions once it had oceans, how would those oceans have formed in the first place? This is where the story gets much more complicated and controversial. For water to condense from vapor into liquid, the atmospheric temperature and pressure have to drop below what's called the saturation point. Early in Venus's history, when volcanic outgassing was pumping enormous amounts of water vapor and carbon dioxide into the atmosphere, the planet might have been far too hot for condensation to occur. Some scientists argue that Venus was caught in what's called a moist greenhouse state from the very beginning. In this scenario, water vapor in the atmosphere acts as such a powerful greenhouse gas that it prevents the planet from cooling enough for oceans to form. The water stays locked in the atmosphere as superheated steam, creating a hellishly hot planet even before the more famous runaway greenhouse effect takes hold. This is where recent research has thrown a wrench into the optimistic models of wet Venus. In December of 2024, a groundbreaking study challenged the entire idea that Venus ever had surface oceans. This research took a completely different approach, focusing not on atmospheric models, but on the interior chemistry of the planet itself. The study examined how water behaves inside rocky planets as they form and evolve. When planets condense from dust and debris, water can be incorporated into their rocks and minerals. This interior water is crucial because it's the source of water vapor that gets released during volcanic outgassing. No interior water means no water vapor. No water vapor means no possibility of oceans, no matter how perfect the atmospheric conditions might be. The researchers used sophisticated models of planetary formation and evolution to ask a critical question. How much water could Venus's interior have contained? Their results suggested that Venus might have formed with a much drier interior than Earth. The closer proximity to the Sun during the planet formation process might have prevented Venus from incorporating significant amounts of water into its rocks. In this dry Venus scenario, the planet never had enough water to form substantial oceans, regardless of what its climate models predicted. The small amounts of water vapor released by early volcanic activity would have been quickly lost to space through a process called hydrodynamic escape, where the entire upper atmosphere essentially boils away. But this dry Venus theory faces a major challenge from chemistry. Venus's atmosphere today contains a smoking gun that suggests the planet once had vastly more water than it does now. The isotopic signature of hydrogen. All water molecules contain hydrogen, but there are two types of hydrogen atoms. Regular hydrogen has one proton in its nucleus. Heavy hydrogen, called deuterium, has one proton and one neutron. Both types behave almost identically in chemical reactions. But there's one crucial difference. Deuterium is twice as heavy as regular hydrogen. When water molecules are split apart by solar radiation high in the atmosphere, the hydrogen atoms can escape to space if they're moving fast enough. Regular hydrogen, being lighter, escapes much more easily than heavy deuterium. Over millions of years, this preferential escape of regular hydrogen leaves the remaining atmospheric water enriched in deuterium. Venus's atmosphere today shows a deuterium to hydrogen ratio that's about 150 times higher than Earth's. This is an extraordinary enrichment that can only be explained by massive hydrogen loss over geological time. When scientists work backward from this ratio, they calculate that Venus must once have had enough water to create a global ocean at least 3 meters deep. Some estimates suggest much more water than that, perhaps enough for oceans hundreds of meters deep. This isotopic evidence strongly supports the idea that Venus was once a much wetter world. But it doesn't tell us whether that water ever existed as liquid oceans or remained trapped as atmospheric steam. The deuterium signature could be the fossil remains of oceans that once sparkled under alien skies, or it could be the chemical ghost of water that was always too hot to condense. Recent measurements from European Space Agency missions have added another piece to this puzzle. The Venus Express spacecraft, which orbited Venus from 2006 to 2014, detected water vapor escaping from the planet's upper atmosphere in real time. The spacecraft observed that Venus is still losing hydrogen to space today, confirming that the water loss process is ongoing. But Venus Express also made another intriguing discovery. The spacecraft detected variations in the water vapor content of Venus's atmosphere that seemed to correlate with solar activity. When the sun was more active, sending more high-energy radiation toward Venus, the planet lost water vapor more rapidly. This suggests that the rate of water loss hasn't been constant over Venus's history. During periods when the young sun was less active, Venus might have lost water much more slowly. This could have provided windows of time when water vapor could accumulate in the atmosphere and potentially condense into surface oceans. But as the sun brightened and became more active over billions of years, these windows of opportunity might have closed forever. The question of ancient Venusian water has implications far beyond just satisfying scientific curiosity. If Venus was once habitable, it represents a cautionary tale of planetary climate change so extreme that it erased all traces of a potentially living world. If Venus was never habitable, it tells us that the conditions for life might be far rarer and more fragile than we hoped. Understanding Venus's water history also affects how we interpret observations of exoplanets. Thousands of planets orbiting other stars have been discovered in what astronomers call the habitable zone, the region around a star where liquid water could theoretically exist. But if Venus teaches us anything, it's that being in the habitable zone is no guarantee of habitability. Many of these exoplanets might be Venus analogues rather than Earth analogues, worlds that appear potentially habitable from a distance but are actually hellish greenhouse planets with no hope of supporting life. The Venus question forces us to be much more careful and skeptical when we evaluate the habitability of distant worlds. So did Venus ever experience the gentle rains that could have filled its first oceans? Did ancient rivers once carve channels across continents, now hidden beneath crushing atmospheres and sulfuric acid clouds? We don't know for certain, but we're closer to an answer than ever before. Upcoming missions to Venus, planned for the late 2020s and early 2030s, will carry instruments specifically designed to resolve this mystery. They'll analyze the composition of Venus's atmosphere with unprecedented precision, study the isotopic signatures of multiple elements, and use advanced radar to probe the planet's surface for geological clues about its watery past. But even as we wait for these missions to provide definitive answers, the question haunts us. Because if Venus was once wet, if it once had a chance to become a second Earth, then something triggered its transformation into the hell world we see today. And understanding that trigger might be the key to ensuring that Earth never follows the same path. Whether or not Venus had oceans, something tipped it toward its doom. Something catastrophic happened to Venus. Whether it started with oceans or remained forever dry, the planet we see today tells the story of a climate system that didn't just fail, it collapsed so completely that it transformed an entire world into something unrecognizable. This wasn't gradual climate change, this was planetary apocalypse. The process that destroyed Venus has a deceptively simple name: the runaway greenhouse effect. But don't let the simplicity fool you. This is one of the most terrifying feedback loops in planetary science, a process so destructive that once it begins, it becomes unstoppable. Understanding how it works is crucial, because the same physical laws that doomed Venus also govern Earth's climate system. To understand what happened to Venus, we need to start with the basics of how greenhouse effects work. When sunlight hits a planet's surface, it warms the ground and oceans. That warm surface then radiates heat back towards space, but not in the same form it arrived. Sunlight comes in as visible light and ultraviolet radiation. The heated surface radiates that energy back as infrared radiation, which we experience as heat. Here's where greenhouse gases become crucial. Certain molecules in the atmosphere, like carbon dioxide and water vapor, are transparent to visible light, but absorb infrared radiation. They act like a blanket, trapping heat that would otherwise escape to space. This is actually a good thing in moderation. Without any greenhouse effect, Earth would be a frozen ball of ice with an average temperature of -18 degrees Celsius. The problem arises when you have too much of a good thing. As greenhouse gas concentrations increase, more heat gets trapped. Surface temperatures rise. And here's where Venus's story becomes a cautionary tale that keeps climate scientists awake at night. Water vapor is itself a greenhouse gas. In fact, it's a very powerful one. As temperatures rise due to carbon dioxide or other greenhouse gases, more water evaporates from oceans and lakes. That additional water vapor in the atmosphere traps even more heat, causing temperatures to rise further, which causes even more evaporation. This is called a positive feedback loop, though there's nothing positive about its consequences. On Earth, this water vapor feedback is kept in check by several factors. Clouds can reflect sunlight back to space, cooling the planet. Rain removes water vapor from the atmosphere. And most importantly, Earth has what scientists call negative feedback mechanisms that help stabilize the climate system. But Venus crossed a threshold where the positive feedbacks overwhelmed any stabilizing mechanisms. Once this happens, the process becomes what scientists call a runaway greenhouse effect. The name is grimly appropriate. Like a runaway train, once the process begins, nothing can stop it until it reaches its devastating conclusion. The runaway greenhouse begins when surface temperatures rise high enough that the oceans start to boil. This doesn't mean the water reaches 100 degrees Celsius everywhere. Even at much lower average temperatures, the most volatile water begins to evaporate rapidly from the warmest regions. That water vapor acts as an incredibly powerful greenhouse gas, trapping more heat and accelerating the warming. As temperatures continue to rise, more and more of the planet's water supply enters the atmosphere as vapor. The atmosphere becomes thick with steam, trapping enormous amounts of heat. Surface temperatures soar beyond the boiling point of water everywhere on the planet. At this point, any remaining liquid water vaporizes almost instantly. But the process doesn't stop there. As temperatures climb past several hundred degrees, other materials begin to vaporize. Limestone and other carbonate rocks, which normally lock up carbon dioxide, begin to break down and release their stored CO2 into the atmosphere. This adds even more greenhouse gas to an already supercharged atmosphere, driving temperatures even higher. Venus today shows us the end result of this process. Surface temperatures reach 465 degrees Celsius. That's hot enough to melt lead, zinc, and tin. The atmospheric pressure is 92 times greater than Earth's, equivalent to being nearly a kilometer underwater in Earth's oceans. The atmosphere is 96.5% carbon dioxide, with clouds of concentrated sulfuric acid. But what triggered this apocalyptic transformation? Scientists have identified several potential culprits, and the reality is probably a combination of all of them working together in a perfect storm of planetary destruction. The first suspect is volcanism on a scale that's hard to imagine. Venus shows evidence of massive volcanic activity throughout its history. The planet's surface is covered with volcanic features: enormous shield volcanoes, vast lava plains, and complex networks of volcanic ridges. Some of these volcanic provinces are larger than entire continents on Earth. The largest volcanic features on Venus are called large igneous provinces. These represent periods when enormous volumes of lava erupted over geologically short time periods. On Earth, similar events have been linked to mass extinctions, but Venus's volcanic activity appears to have been far more extensive and long-lasting than anything Earth has experienced. These massive eruptions would have pumped gigatons of carbon dioxide and sulfur dioxide into Venus's atmosphere. A single large eruption might have released as much CO2 as human civilization has produced in the past century. Multiple eruptions occurring over millions of years would have fundamentally altered the atmospheric composition of the entire planet. The sulfur dioxide is particularly important because it creates sulfuric acid when it combines with water vapor in the atmosphere. This acid rain would have been far more corrosive than anything Earth experiences today. It might have accelerated the weathering of surface rocks, releasing even more CO2 into the atmosphere and adding to the greenhouse effect. But volcanism alone might not have been enough to trigger a full runaway greenhouse. Venus needed another push, and that push came from an unlikely source: the Sun itself. When the Sun first formed 4.5 billion years ago, it was about 30% dimmer than it is today. This is called the faint young sun paradox, and it affects how we understand the early climate history of all the inner planets. As stars like our Sun age, they gradually become brighter and hotter. This solar brightening occurs very slowly by human standards, but over billions of years, it represents a significant increase in the energy reaching the planets. For Earth, solar brightening has been partially offset by the gradual removal of CO2 from our atmosphere through geological processes. As the Sun got brighter, Earth's carbon cycle helped keep global temperatures relatively stable by reducing the greenhouse effect. But Venus apparently couldn't make this adjustment. As the Sun brightened, Venus received more and more energy. At some point, probably between 1 and 2 billion years ago, the incoming solar energy crossed what scientists call the moist greenhouse threshold. This is the point where water vapor in the atmosphere becomes so abundant that it prevents the planet from radiating enough heat to space to maintain stable temperatures. Once Venus crossed this threshold, the runaway greenhouse became inevitable. The additional solar energy began evaporating more water from any remaining oceans or ice. That water vapor trapped more heat, which evaporated more water, which trapped more heat, in an accelerating cycle that couldn't be stopped. Computer models suggest that once the runaway greenhouse begins, it proceeds with terrifying speed on geological timescales. Within a few million years, all of a planet's water can be vaporized into the atmosphere. Within a few tens of millions of years, that water can be completely lost to space, leaving behind the kind of desiccated hell world we see today. The runaway greenhouse also explains one of Venus's most puzzling features: its incredibly thick atmosphere. Earth's atmosphere has a mass of about 5 times 10 to the 18th power kilograms. Venus's atmosphere has a mass of about 5 times 10 to the 20th power kilograms. That's 90 times more massive than Earth's entire atmosphere. Where did all that gas come from? Much of it was probably water vapor that got trapped during the runaway greenhouse phase. Even after the hydrogen escaped to space and the oxygen was absorbed by surface rocks, the sheer volume of gas that had been added to the atmosphere during the runaway phase remained. Additional CO2 from volcanic outgassing and the breakdown of carbonate rocks added to this massive atmospheric envelope. But the runaway greenhouse might not have been triggered by volcanism and solar brightening alone. Some scientists suggest that Venus's slow rotation played a crucial role in its downfall. While slow rotation might have helped maintain habitable conditions early in Venus's history, it might have also made the planet more vulnerable to catastrophic climate change. On Earth, our rapid rotation helps distribute heat around the planet. Warm air from the equator is transported toward the poles, while cold air from high latitudes moves toward the equator. This circulation helps prevent extreme temperature differences between different regions of the planet. Venus's slow rotation creates a very different circulation pattern. The planet essentially has one giant circulation cell in each hemisphere, with air rising at the equator and sinking at the poles. This circulation pattern might have been less effective at distributing heat around the planet, allowing some regions to become extremely hot while others remained cooler. If the runaway greenhouse began in the hottest regions first, those areas would have started pumping water vapor into the global atmosphere. Once that water vapor began circulating around the planet, it would have created greenhouse warming everywhere, even in regions that had previously been cool enough to support liquid water. The timing of Venus's runaway greenhouse is still hotly debated among scientists. Some models suggest it happened very early in Venus's history, perhaps within the first few 100 million years after the planet formed. Other models suggest Venus might have remained habitable for up to 2 billion years before crossing the fatal threshold. The timing matters enormously for how we think about habitability in the universe. If Venus lost its habitability very early, it suggests that conditions suitable for life are incredibly rare and fragile. If Venus remained habitable for billions of years before succumbing to the runaway greenhouse, it suggests that habitable conditions might be more common, but also more temporary than we'd like to believe. Recent research has also revealed that the runaway greenhouse effect might be even more devastating than previously thought. Advanced climate models show that once the process begins, it doesn't just destroy existing habitable conditions. It can actually prevent a planet from ever recovering habitability, even if conditions change. This is because the runaway greenhouse doesn't just remove water from the surface. It removes water from the entire planet permanently. The water gets split into hydrogen and oxygen high in the atmosphere. The hydrogen escapes to space, carrying away the raw material needed to make water. Even if Venus somehow cooled down in the future, it would remain a dry, lifeless world because the water needed for oceans and life is gone forever. This permanent destruction of habitability has profound implications for astrobiology and the search for life elsewhere in the universe. It suggests that potentially habitable planets might have narrow windows of opportunity for life to emerge and evolve. Miss that window, and the planet might be doomed to permanent sterility. Understanding the runaway greenhouse effect on Venus isn't just an academic exercise. It's a stark reminder of how quickly and completely planetary climate systems can collapse. While Earth is not in immediate danger of experiencing a Venus-style runaway greenhouse, the physics that destroyed Venus also govern our planet's climate system. The runaway greenhouse represents the ultimate climate tipping point, a line that once crossed leads to the complete transformation of a world. Venus crossed that line billions of years ago, and the scars of that crossing are written in every breath of its poisonous atmosphere and every degree of its hellish surface temperature. What followed wasn't just heating, it was planetary collapse. The runaway greenhouse effect was just the beginning of Venus's transformation into hell. What followed was a systematic destruction of everything that might have made the planet habitable, a planetary death spiral that played out over hundreds of millions of years. This is the story of how Venus lost not just its water, but its very ability to protect what remained of its atmosphere from the hostile environment of space. To understand how completely Venus lost its water, we need to journey to the very edge of space itself, to the thin boundary where a planet's atmosphere meets the vacuum of the cosmos. This is where one of the most important battles in planetary science plays out. The fight between a world trying to hold on to its atmosphere and a star trying to strip it away. High above Venus's surface, about 100 to 150 kilometers up in what scientists call the thermosphere, something violent and continuous has been happening for billions of years. Here, the sun's ultraviolet radiation strikes water vapor molecules with enough energy to literally tear them apart. This process, called photodissociation, splits each water molecule into its component parts: 2 hydrogen atoms and 1 oxygen atom. On Earth, this same process occurs, but most of the hydrogen and oxygen atoms eventually recombine to form water again. The products of photodissociation don't escape easily because Earth has protective mechanisms that Venus lacks. But on Venus, these atoms face a very different fate. The hydrogen atoms produced by photodissociation are incredibly light. In the thin upper atmosphere, where gas molecules are spread far apart, these hydrogen atoms can reach tremendous speeds due to thermal motion. Some of them reach what scientists call escape velocity, the minimum speed needed to break free from Venus's gravitational pull and disappear into space forever. Venus's gravity is strong, about 90% as strong as Earth's, but it's not strong enough to hold onto the lightest elements when they're energized by intense solar radiation. One by one, hydrogen atoms have been streaming away from Venus into space, carrying with them the raw material needed to make water. But hydrogen doesn't escape alone. Venus faces an even more devastating process that Earth largely avoids, thanks to one crucial difference between the two planets. Earth has a magnetic field, and Venus essentially does not. Earth's magnetic field is generated deep in the planet's core, where a layer of molten iron flows in complex patterns driven by our planet's rotation. This flowing iron acts like a giant dynamo, generating electrical currents that create a magnetic field extending far into space. This magnetic field, called the magnetosphere, acts like an invisible shield protecting Earth's atmosphere from the solar wind. The solar wind is a constant stream of charged particles, mostly protons and electrons, flowing away from the sun at speeds of several hundred kilometers per second. When these particles encounter Earth's magnetic field, they're deflected around our planet, creating the beautiful auroras we see at the poles but leaving most of our atmosphere undisturbed. Venus tells a very different story. The planet rotates incredibly slowly, taking 243 Earth days to complete a single rotation. This sluggish spin means that Venus's molten iron core can't generate the complex flow patterns needed to sustain a strong magnetic field. Venus does have a very weak magnetic field, but it's thousands of times weaker than Earth's, far too weak to provide any meaningful protection from the solar wind. Without a magnetic shield, Venus's upper atmosphere is completely exposed to the full force of the solar wind. The charged particles streaming from the sun slam directly into Venus's atmosphere, transferring energy to atmospheric molecules and literally blowing them away into space. This process, called atmospheric escape, has been stripping away Venus's atmosphere for billions of years. The European Space Agency's Venus Express mission, which orbited Venus from 2006 to 2014, provided the first detailed observations of this atmospheric escape in action. The spacecraft carried instruments that could detect individual ions, electrically charged atoms and molecules, as they were torn away from Venus and hurled into space. What Venus Express discovered was both fascinating and terrifying. The spacecraft observed massive plumes of oxygen ions streaming away from Venus's night side, where the planet's weak magnetic field lines get stretched and twisted by the solar wind. These oxygen ions were the remnants of water molecules that had been split apart by solar radiation. The hydrogen had already escaped, and now the oxygen was following it into the void. But the loss wasn't limited to just hydrogen and oxygen. Venus Express detected ions of many other elements being stripped away: carbon, sulfur, and even heavier elements that should have been much harder for the solar wind to remove. Venus was literally bleeding its atmosphere into space. The rate of this atmospheric loss is staggering. Venus Express measured that Venus is currently losing about twice as much hydrogen per second as Earth loses, despite having much less water vapor in its atmosphere. For heavier ions like oxygen, the loss rate is even more dramatic. Venus loses oxygen to space at a rate about 10 times higher than Earth. Over geological timescales, these seemingly small losses add up to planetary catastrophe. Computer models based on Venus Express data suggest that Venus has lost the equivalent of a global ocean several meters deep to atmospheric escape. Some estimates push this number much higher, suggesting that Venus might have lost enough water to fill oceans hundreds of meters deep. But atmospheric escape doesn't just remove water, it fundamentally changes the chemistry of what remains. Remember that deuterium, heavy hydrogen, is much harder for the solar wind to strip away than regular hydrogen. Over billions of years of preferential regular hydrogen loss, Venus's remaining water vapor has become incredibly enriched in deuterium. Today, the deuterium to hydrogen ratio in Venus's atmosphere is about 150 times higher than Earth's. This isotopic signature is like a chemical fossil, preserving evidence of the massive hydrogen loss that has occurred over the planet's history. Every molecule of water vapor in Venus's atmosphere today tells the story of thousands of molecules that have been lost to space. The oxygen atoms left behind after hydrogen escape faced their own complex fate. Some oxygen was stripped away by the solar wind, as Venus Express observed, but much of it underwent chemical reactions with Venus's surface rocks. This process, called oxidation, locked oxygen into iron oxides and other minerals in Venus's crust. Ironically, Venus's surface rocks are probably much more oxidized than Earth's, despite the planet's lack of free oxygen in its atmosphere. This oxygen, trapped in minerals, represents another chemical fossil of Venus's watery past. If we could somehow extract and analyze these oxidized surface materials, they might tell us even more about how much water Venus once possessed. The loss of Venus's magnetic field had consequences beyond just atmospheric escape. Without magnetic protection, Venus's surface is constantly bombarded by cosmic rays and solar particles that would be deflected by a strong magnetosphere. This radiation environment makes Venus's surface even more hostile to any potential life than the extreme temperature and pressure alone would suggest. The absence of a magnetic field also affects how Venus interacts with the solar wind in other ways. When the solar wind encounters Venus, it creates what scientists call an induced magnetosphere, a temporary magnetic field formed by the interaction between the solar wind and Venus's ionosphere. This induced field provides some limited protection, but it's highly variable and much weaker than a planet-generated magnetic field. Venus Express observed that this induced magnetosphere changes dramatically depending on solar activity. During periods of intense solar storms, when the solar wind is particularly strong, Venus's atmospheric loss rates increase significantly. This suggests that Venus has lost atmosphere more rapidly during periods of high solar activity throughout its history. The implications are sobering. Early in the solar system's history, when the Sun was younger and more active, Venus might have experienced even more intense atmospheric stripping than it does today. This could have accelerated the loss of water and other volatile compounds, making Venus's transformation into a hell world even more rapid than current models suggest. The death of Venus's magnetic field also reveals something important about planetary evolution. Earth maintains its magnetic field because our planet has remained geologically active, with plate tectonics helping to keep the core hot and fluid. Venus shows no clear evidence of plate tectonics. Its surface appears to be a single solid shell with no moving plates. This geological difference might be both a cause and consequence of Venus's atmospheric evolution. Without plate tectonics to recycle materials between the surface and interior, Venus couldn't regulate its atmospheric composition the way Earth does. And without a thick atmosphere to insulate the planet's interior, Venus might have cooled more rapidly, shutting down the geological processes needed to maintain a magnetic field. The story of Venus's magnetic field loss also highlights how interconnected planetary systems really are. The magnetic field, the atmosphere, the surface geology, and even the rotation rate are all linked in complex ways. Change one component, and it can trigger cascading effects throughout the entire planetary system. For Venus, the loss of magnetic protection created a feedback loop that accelerated its atmospheric demise. As the solar wind stripped away the atmosphere, the planet lost insulation, causing the interior to cool and weakening any remaining magnetic field generation. A weaker magnetic field allowed even more atmospheric escape, which further reduced atmospheric pressure and insulation. This downward spiral continued for billions of years, until Venus reached the state we observe today. A planet with virtually no magnetic field, an atmosphere under constant assault from the solar wind, and a surface environment so extreme that it represents the complete opposite of habitability. But perhaps the most chilling aspect of Venus's atmospheric death is how irreversible it appears to be. Even if Venus somehow moved to a more favorable orbit, even if the Sun dimmed to more comfortable levels, the planet couldn't recover its lost water. The hydrogen needed to make water molecules is gone, scattered across the solar system by billions of years of solar wind stripping. Venus's fate reveals the fragility of planetary atmospheres and the crucial importance of magnetic fields for maintaining habitability over geological timescales. It's a lesson that extends far beyond our solar system, affecting how we evaluate the potential habitability of the thousands of exoplanets being discovered around other stars. Many of these distant worlds might be experiencing their own versions of atmospheric escape, slowly losing their potential for habitability to their host star's radiation and particle winds. Understanding Venus's atmospheric death might be key to identifying which exoplanets have the best chance of maintaining habitable conditions over the billions of years needed for complex life to evolve. The death of water and magnetism on Venus wasn't just a planetary tragedy. It was a lesson written in isotopes and magnetic field lines, a warning about how quickly the conditions for life can disappear when a planet loses its protective mechanisms. Venus stands as a monument to atmospheric vulnerability, a world that shows us what happens when the delicate balance that maintains habitability is broken beyond repair. So why didn't Earth meet the same fate? Earth and Venus began as twins, but only one survived to tell the tale. Understanding why Earth avoided Venus's catastrophic fate isn't just a matter of scientific curiosity. It's the key to understanding how rare and precious our world truly is, and what factors determine whether a planet can maintain the delicate conditions necessary for life across billions of years. The story of Earth's survival begins deep in our planet's core, nearly 6,400 kilometers beneath our feet. Here, in a realm of crushing pressure and temperatures exceeding 5,000 degrees Celsius, liquid iron flows in complex patterns that have been protecting our world for over 3 billion years. This is where Earth's magnetic field is born, and it's the first and perhaps most crucial reason why our planet didn't follow Venus down the path to atmospheric destruction. Earth's magnetic field exists because our planet spins rapidly, completing one rotation every 24 hours. This fast rotation, combined with convection currents in the molten outer core, creates what scientists call a geodynamo. Imagine the Earth's core as a massive electrical generator, with flowing liquid iron acting as the conductor. The rotation and convection create electrical currents, and those currents generate the magnetic field that extends far into space around our planet. This magnetic field, invisible but absolutely vital, creates what we call the magnetosphere. It's a protective bubble that deflects most of the solar wind away from Earth's atmosphere. When charged particles from the sun encounter our magnetic field, they're guided around our planet rather than slamming directly into our atmosphere. Some particles do make it through near the magnetic poles, creating the beautiful auroras we see dancing across polar skies. But the vast majority of the solar wind is deflected harmlessly away. Venus, rotating once every 243 Earth days, simply cannot generate this kind of protection. The sluggish rotation means that convection currents in its core, if they exist at all, cannot organize into the complex patterns needed to sustain a strong magnetic field. Without this magnetic shield, Venus has been defenseless against solar wind stripping for billions of years. But Earth's magnetic field protection goes beyond just deflecting the solar wind. Our magnetosphere also helps trap and retain atmospheric gases that might otherwise escape to space. The magnetic field lines act like invisible highways, guiding charged particles in complex paths around our planet rather than allowing them to stream away into space. This magnetic bottle effect helps Earth hold onto its atmosphere even when solar activity is high. The strength of Earth's magnetic field has varied throughout our planet's history, sometimes weakening significantly and even reversing direction completely. During these periods of magnetic weakness, Earth has experienced higher rates of atmospheric escape. But our magnetic field has never disappeared entirely for long periods, unlike Venus, which appears to have lost its magnetic protection permanently early in its history. However, magnetic field protection alone wouldn't have been enough to save Earth. Our planet had to develop additional mechanisms to regulate its climate and atmosphere over geological timescales. The most important of these mechanisms is something Venus completely lacks: plate tectonics. Earth's surface is broken into about 15 major plates that slowly move across the planet's surface at rates of a few centimeters per year. These plates collide, separate, and slide past each other in a complex dance that has been reshaping our planet's surface for billions of years. This might seem like a purely geological process, but plate tectonics is actually the foundation of Earth's long-term climate stability. Here's how it works. When it rains on Earth, carbon dioxide from the atmosphere dissolves in the rainwater, creating weak carbonic acid. This slightly acidic rain weathers rocks, breaking down silicate minerals and washing the products into the ocean. In the ocean, marine organisms use the dissolved carbon and other materials to build shells and skeletons made of calcium carbonate. When these organisms die, their remains settle to the seafloor, locking carbon away in sedimentary rocks. Over millions of years, these carbon-rich sediments get pushed by plate tectonics to subduction zones. places where one plate slides beneath another into the hot interior of the planet. The heat and pressure of subduction cause the carbonate minerals to break down, releasing CO2 back into the atmosphere through volcanic eruptions. This completes what scientists call the carbon cycle, a planetary thermostat that has kept Earth's climate relatively stable for billions of years. When Earth gets too hot, more water evaporates, leading to more rainfall and more rapid weathering of rocks. This removes more CO2 from the atmosphere, cooling the planet. When Earth gets too cold, weathering slows down, allowing volcanic CO2 to build up in the atmosphere and warm the planet. It's an automatic climate control system powered by plate tectonics. Venus shows no clear evidence of plate tectonics. Its surface appears to be a single solid shell with no moving plates. Without this recycling mechanism, Venus couldn't regulate its atmospheric CO2 concentration. Once volcanic outgassing or other processes began pumping large amounts of CO2 into Venus's atmosphere, there was no efficient way to remove it. The carbon just accumulated, creating the thick CO2 atmosphere that eventually triggered the runaway greenhouse effect. The absence of plate tectonics on Venus might be both a cause and consequence of its atmospheric evolution. Early loss of water through atmospheric escape might have made Venus's interior less fluid, preventing the development of plate tectonics. Without plate tectonics to recycle water and other volatiles back into the interior, Venus couldn't maintain the geological processes needed to regulate its atmosphere. Earth's rapid rotation also plays a crucial role beyond just generating our magnetic field. Our 24-hour day creates complex atmospheric circulation patterns driven by the Coriolis effect. This rotation-powered circulation helps distribute heat around the planet, preventing extreme temperature differences between different regions. On Earth, warm air rises at the equator and moves toward the poles, while cold air flows from the poles toward the equator. This global circulation, combined with ocean currents also driven by rotation, helps maintain relatively moderate temperatures across most of the planet's surface. Even our polar regions, despite receiving much less sunlight than the equator, remain warm enough for liquid water to exist. Venus's extremely slow rotation creates very different circulation patterns. With such a long day-night cycle, Venus essentially has just one giant circulation cell in each hemisphere. Air heated at the equator rises and flows toward the poles, while air at the poles sinks and flows back toward the equator. This simple circulation pattern is much less efficient at distributing heat around the planet. This inefficient heat distribution might have contributed to Venus's climate instability. If some regions of early Venus became much hotter than others, those hotspots might have begun the runaway greenhouse process, even while other parts of the planet remained cool. Once water vapor from the hot regions entered the global atmosphere, it would have created greenhouse warming everywhere, eventually triggering planet-wide climate collapse. Earth also benefited from having a large moon, something Venus lacks entirely. Our moon, formed early in Earth's history through a giant impact, has helped stabilize our planet's axial tilt over geological timescales. Earth's axis is tilted about 23.5 degrees relative to our orbital plane, creating our seasons. Without the moon's gravitational influence, this tilt would vary chaotically over millions of years, potentially creating extreme climate instability. The moon also drives Earth's tides, which might have played a role in the evolution of life by creating tidal pools and other environments where complex chemistry could occur. The tidal forces also help drive mixing in Earth's oceans, distributing heat and nutrients around the planet. But perhaps most importantly, Earth's moon might have helped our planet maintain its rapid rotation. The angular momentum locked up in the Earth-Moon system has helped prevent Earth from slowing down as much as it otherwise might have due to solar tides. Without our moon, Earth might rotate much more slowly today, possibly too slowly to maintain a strong magnetic field. The timing of Earth's formation and early evolution also played a crucial role in our survival. Earth formed at just the right distance from the Sun to receive moderate amounts of solar energy. Too close, like Venus, and the increased energy input would have made it impossible to maintain stable surface water. Too far, like Mars, and the planet would have been too cold and too small to maintain a thick atmosphere. Earth also formed with the right composition to maintain geological activity over billions of years. Our planet contains enough radioactive elements like uranium, thorium, and potassium to provide internal heat through radioactive decay. This internal heat source, combined with heat left over from Earth's formation, has kept our planet's interior molten and active, driving both the magnetic field generating dynamo and the plate tectonics that regulate our climate. The presence of life itself has also helped stabilize Earth's climate through various feedback mechanisms. Plants and other photosynthetic organisms remove CO2 from the atmosphere, helping prevent runaway greenhouse conditions. The evolution of oxygen-producing photosynthesis created our oxygen-rich atmosphere, which forms the ozone layer that protects the surface from harmful ultraviolet radiation. Life also participates in the carbon cycle through processes like the formation of limestone by marine organisms. In a sense, life has become part of Earth's climate regulation system, helping maintain the conditions that allow life to continue existing. But Earth's survival story also includes some close calls that remind us how fragile planetary habitability really is. During the period known as Snowball Earth, which occurred several times between 800 million and 550 million years ago, our planet nearly froze completely. Ice sheets extended from the poles almost to the equator, and global average temperatures dropped far below freezing. Earth escaped these snowball conditions partly through volcanic outgassing that gradually built up CO2 in the atmosphere until greenhouse warming could melt the ice. But if the snowball periods had lasted longer, or if Earth had been slightly farther from the Sun, our planet might have remained permanently frozen, ending any chance for complex life to evolve. Earth has also experienced several mass extinction events where climate changes, often triggered by massive volcanic eruptions or asteroid impacts, killed off large percentages of existing species. The most famous of these, the extinction that killed the dinosaurs 66 million years ago, was caused by an asteroid impact that temporarily disrupted Earth's climate system. While these events were catastrophic for life, they weren't severe enough to trigger a Venus-style climate collapse. The story of why Earth survived while Venus perished isn't just about luck. It's about the complex interplay of multiple factors: magnetic field protection, plate tectonics, appropriate rotation rate, the right distance from the Sun, the presence of a large moon, and the right internal composition to maintain geological activity over billions of years. Each of these factors alone might not have been sufficient. It's the combination of all of them working together that has allowed Earth to maintain habitable conditions for over 3 billion years. Remove any one of these protective mechanisms, and Earth might have followed a very different evolutionary path. This understanding has profound implications for how we think about habitability in the universe. It suggests that truly habitable planets like Earth might be much rarer than we initially hoped. A planet can't just be in the habitable zone around its star. It needs the right size, the right composition, the right rotation rate, plate tectonics, magnetic field protection, and perhaps even the right kind of moon. The rarity of these conditions makes Earth's survival story even more remarkable. We live on a planet that won a cosmic lottery, a world that managed to maintain the delicate balance needed for life across billions of years of solar system evolution. Understanding why Earth survived while Venus failed helps us appreciate just how special our world really is. But Earth's survival story also contains warnings. The same processes that destroyed Venus still operate in Earth's climate system. While we're not in immediate danger of a runaway greenhouse effect, Human activities are adding greenhouse gases to our atmosphere at unprecedented rates. Understanding Venus's fate reminds us that planetary climate systems can undergo rapid, irreversible changes when pushed beyond certain thresholds. Venus didn't just fail, it warned us what happens when climate spirals beyond repair. Venus stands as the ultimate cautionary tale in our solar system, a world that shows us what happens when a planet's climate system doesn't just change, but collapses entirely. The lessons written in Venus's poisonous atmosphere and molten surface aren't just ancient history. They're a roadmap for understanding climate change, tipping points, and the fragile balance that keeps worlds habitable. In Venus's fate, we can read warnings that apply directly to Earth's future, and to every potentially habitable world we've discovered orbiting distant stars. To understand why Venus matters for Earth's climate future, we need to grasp just how similar the underlying physics are between the two planets. The greenhouse effect that turned Venus into a hell world operates according to the same physical laws that govern Earth's climate. Carbon dioxide traps heat in Earth's atmosphere using exactly the same molecular processes that trap heat in Venus's atmosphere. Water vapor amplifies warming on Earth through the same feedback mechanisms that help destroy Venus. The difference isn't in the physics. The difference is in the degree. On Earth today, carbon dioxide makes up about 420 parts per million of our atmosphere, or roughly 0.04%. This tiny fraction is enough to keep our planet about 33 degrees Celsius, warmer than it would be without any greenhouse effect at all. Without this warming, Earth's average temperature would be about minus 18 degrees Celsius, cold enough to freeze the ocean solid. Venus's atmosphere, by contrast, is 96.5% carbon dioxide. That's nearly 2,400 times more concentrated than Earth's CO2 levels. This massive difference in concentration is what creates Venus's 465 degrees Celsius surface temperature compared to Earth's comfortable 15 degrees Celsius average. But here's what should keep us awake at night. The transition from Earth-like to Venus-like doesn't require reaching Venus's current CO2 levels. Climate models show that there are thresholds, called tipping points, where relatively small additional changes can trigger much larger, potentially irreversible transformations. On Earth, we're already seeing examples of these tipping points beginning to activate. In the Arctic, warming temperatures are melting sea ice, exposing dark ocean water that absorbs more sunlight than reflective ice. This creates additional warming, which melts more ice, in a feedback loop that's accelerating Arctic warming far beyond the global average. Permafrost, permanently frozen soil that covers vast areas of the northern hemisphere, contains enormous amounts of carbon locked up in frozen organic matter. As temperatures rise, this permafrost is beginning to thaw, releasing methane and carbon dioxide into the atmosphere. Methane is a particularly potent greenhouse gas, with a warming effect about 28 times stronger than CO2 over a 100-year period. These feedback processes on Earth work according to the same principles that amplified warming on Venus. The difference is that Earth's feedbacks are still relatively small and slow compared to what Venus experienced. But they're real, they're measurable, and they're accelerating. The most concerning parallel between Earth and Venus lies in the potential role of water vapor feedback. As Earth's atmosphere warms due to increased CO2 from human activities, more water evaporates from oceans, lakes, and rivers. Water vapor is itself a powerful greenhouse gas, so this additional moisture in the atmosphere traps more heat, causing further warming and more evaporation. On Venus, this water vapor feedback became catastrophic, eventually leading to complete ocean evaporation and runaway climate change. Earth is nowhere near this extreme, but we're already seeing water vapor feedback contributing to current warming. Climate models consistently show that water vapor feedback roughly doubles the warming effect of CO2 increases alone. The question that haunts climate scientists is this: Are there conditions under which Earth could experience something resembling Venus's runaway greenhouse effect? The answer is both reassuring and terrifying. The reassuring part is that Earth would need to warm by at least several tens of degrees Celsius before approaching the kind of runaway greenhouse that destroyed Venus. Current projections for human-caused climate change, while serious, fall far short of this threshold. Even in the most extreme warming scenarios, Earth is not expected to become Venus like within the next few centuries. The terrifying part is that there are other, more subtle ways that Earth could cross climate tipping points that, while not as extreme as Venus's fate, could still fundamentally transform our planet's habitability. These scenarios have been dubbed soft Venus outcomes, climate changes severe enough to make large parts of Earth uninhabitable, even if they don't boil away the oceans. One such scenario involves the potential collapse of major ice sheets in Greenland and Antarctica. These ice sheets contain enough water to raise global sea levels by over 70 meters if they melted completely. While complete melting would take centuries or millennia, even partial collapse could raise sea levels by several meters, flooding coastal cities that house billions of people. The ice sheet collapse process exhibits the same kind of feedback mechanisms that operated on Venus. As ice sheets melt, they expose darker land or ocean surfaces that absorb more solar energy than reflective ice. This absorption causes more warming and more melting, potentially creating irreversible collapse, even if greenhouse gas concentrations eventually stabilize. Another soft Venus scenario involves changes to atmospheric circulation patterns. Earth's current climate relies on stable patterns of air and ocean circulation that distribute heat around the planet. These circulation patterns are driven by temperature differences between different regions, particularly between the equator and the poles. As the Arctic warms faster than other regions, these temperature differences are decreasing. This is already affecting the jet stream, the high-altitude river of air that guides weather patterns across North America and Europe. A weaker, more meandering jet stream can cause extreme weather events, heat domes that park over regions for weeks, polar vortex events that bring Arctic cold to lower latitudes, and persistent drought or flooding patterns. If these circulation changes become severe enough, they could create regional climates unlike anything in human history. Some areas might become too hot and humid for human survival during parts of the year, even in the shade, with unlimited water. Other areas might experience such severe droughts that agriculture becomes impossible. These changes wouldn't make Earth-Venus like globally, but they could make large portions of our planet uninhabitable. Venus also teaches us about the irreversibility of extreme climate change. Once Venus crossed certain thresholds, particularly the loss of its water to space, the planet became permanently uninhabitable. Even if Venus somehow cooled down in the future, it couldn't recover its oceans because the water needed to make them no longer exists on the planet. Earth faces its own irreversibility thresholds that, while less extreme than Venus's, could still permanently alter our world. The collapse of major ice sheets might be irreversible on human timescales, even if we eventually reduce greenhouse gas concentrations. The extinction of species due to rapid climate change is permanently irreversible. The transformation of ecosystems like coral reefs or Amazon rainforest into completely different systems might persist for thousands of years, even after climate conditions stabilize. Perhaps most importantly, Venus demonstrates how quickly planetary climate systems can change once they cross critical thresholds. While Venus's transformation took millions of years, which seems slow by human standards, it was incredibly rapid by geological standards. Earth's climate system is capable of similarly rapid changes when pushed hard enough. We've already seen examples of this rapid climate response in Earth's geological history. The Paleocene-Eocene thermal maximum, which occurred about 56 million years ago, saw global temperatures rise by 5 to 8 degrees Celsius in less than 20,000 years due to massive carbon emissions from volcanic activity and other sources. While 20,000 years is much longer than human civilizations last, it's an eye blink in geological time. The concerning aspect of current human-caused climate change is its unprecedented speed. We're adding carbon dioxide to the atmosphere at rates far faster than most natural processes. The current rate of CO2 increase is about 100 times faster than typical geological rates of change. This rapid pace gives Earth's natural systems less time to adapt and creates greater risk of crossing tipping points before we can respond. Venus's story also reveals the importance of understanding planetary boundaries, the safe operating limits for Earth's climate system. Just as Venus had thresholds beyond which climate change became unstoppable, Earth has boundaries that, once crossed, could lead to climate states very different from the stable conditions human civilization developed under. Some scientists argue that we've already crossed some of these boundaries. Atmospheric CO2 levels have risen from about 280 parts per million before the Industrial Revolution to over 420 parts per million today. This is the highest CO2 concentration in over 3 million years, well before human ancestors existed. The rate of species extinction has accelerated to levels not seen since the major extinction events in Earth's geological history. Ocean chemistry is changing as the seas absorb excess CO2, making the water more acidic and threatening marine ecosystems. These changes might not lead to Venus-style climate collapse, but they represent fundamental alterations to the Earth system that could persist for thousands of years. Understanding Venus helps us recognize that climate change isn't just about gradual warming. It's about the risk of system-wide transformations that could fundamentally alter how our planet works. Venus experienced the most extreme version of such a transformation, but Earth is capable of its own dramatic climate shifts that, while less severe than Venus's fate, could still revolutionize life on our planet. This perspective makes Venus more than just a scientific curiosity. Venus becomes a laboratory for understanding how planetary climate systems can fail and how quickly habitable worlds can transform into uninhabitable ones. The physics that destroyed Venus are still operating throughout the universe, threatening other worlds and reminding us of the fragility of the conditions that allow life to flourish. But Venus's lessons extend beyond just climate change on Earth. They fundamentally alter how we think about habitability throughout the cosmos, and particularly how we evaluate the thousands of exoplanets being discovered around other stars. Many worlds that appear potentially habitable from a distance might actually be Venus analogues, planets that crossed climate tipping points and became permanent hell worlds despite starting with Earth-like conditions. The implications are staggering. Venus suggests that the universe might be filled with failed Earths, worlds that had every opportunity to become havens for life, but instead became cautionary tales about the fragility of habitability. Understanding this cosmic Venus trap might be crucial for identifying which distant worlds truly have the potential to host life, and which are merely mirages of habitability hiding hellish realities. If Venus teaches us about Earth, it also warns us about what's out there. Venus has taught us one of the most unsettling lessons in astrobiology. A planet can look habitable from space while hiding a hellish reality beneath its clouds. This revelation has profound implications for our search for life beyond our solar system, because the same processes that destroyed Venus are likely operating around countless other stars throughout the galaxy. We may be living in a universe where Venus analogues vastly outnumber Earth analogues, where most potentially habitable worlds are actually elaborate cosmic deceptions. Since 1995, astronomers have discovered over 5,000 planets orbiting other stars. These exoplanets come in an amazing variety of sizes, compositions, and orbital configurations. Many orbit within what we call the habitable zone, also known as the Goldilocks zone, the region around a star where temperatures are just right for liquid water to exist on a planet's surface. The habitable zone concept seems straightforward. Too close to the star and water boils away. Too far and water freezes solid. Somewhere in between lies the sweet spot where oceans can exist and life might flourish. Earth sits comfortably within our sun's habitable zone, while Venus is just inside its inner edge and Mars is near its outer edge. But Venus reveals a crucial flaw in this simple picture. Being in the habitable zone is no guarantee of habitability. Venus sits tantalizingly close to the sun's habitable zone by most definitions, and some climate models suggest it should have been able to maintain surface water for billions of years. Yet Venus became a hell world, while Earth, also in the habitable zone, became a paradise. This realization has led astronomers to define something called the Venus zone, a region around stars where planets might initially appear habitable, but are actually in the process of, or have already undergone, runaway greenhouse warming. The Venus zone typically lies between the habitable zone and the star, representing a treacherous region where planets can become permanently sterilized by climate collapse. The boundaries of the Venus zone depend on many factors: the brightness and age of the star, the planet's size and composition, its rotation rate, and whether it has a magnetic field. For Sun-like stars, the Venus zone might extend from about 0.7 to 0.95 astronomical units, encompassing a significant region where planets might appear habitable from a distance, but are actually undergoing or have completed Venus-style climate catastrophes. Here's where the problem becomes truly concerning for exoplanet science. Many of our current methods for studying distant planets would have difficulty distinguishing between an Earth analog and a Venus analog. When we observe exoplanets, we're typically looking at them from hundreds or thousands of light years away, seeing only the faintest traces of their existence as they transit in front of their host stars or cause tiny wobbles in stellar motion. From such distances, a planet with thick clouds and high reflectivity might look very promising. Venus, viewed from another star system, would appear to have a thick atmosphere and high albedo, characteristics that could be interpreted as evidence of water clouds and a potentially habitable climate. The extreme surface conditions would be completely hidden beneath the cloud deck. Even spectroscopic analysis of exoplanet atmospheres, our most sophisticated technique for studying distant worlds, could be fooled by Venus analogues. Water vapor in the upper atmosphere of a runaway greenhouse planet might create spectral signatures similar to those expected from a habitable world with active water cycles. The challenges go beyond just misidentifying Venus analogues as habitable worlds. We're also discovering that many potentially habitable exoplanets exist in environments that make them even more vulnerable to Venus-style climate collapse than Venus itself was. Many exoplanets orbit red dwarf stars, which are smaller, cooler, and longer lived than our Sun. Red dwarfs make up about 75% of all stars in our galaxy, so planets orbiting them represent a huge fraction of potentially habitable worlds. But red dwarf systems present unique challenges for maintaining habitability. To receive enough energy for liquid water, planets orbiting red dwarfs must orbit very close to their host stars, typically completing an orbit in just days or weeks rather than a full year like Earth. This close proximity means these planets are likely tidally locked, with one side permanently facing the star and the other side in eternal darkness. Tidal locking creates extreme temperature differences between the day and night sides of the planet. The day side might be hot enough to vaporize water, while the night side could be cold enough to freeze out the entire atmosphere. These extreme conditions make it much more difficult to maintain stable, planet-wide climates suitable for liquid water. Even worse, red dwarf stars are notorious for producing powerful stellar flares, sudden bursts of high-energy radiation that can be thousands of times stronger than anything our Sun produces. These flares can strip away planetary atmospheres over time, especially for planets orbiting so close to their host stars. A planet might start with Earth-like conditions, but gradually lose its atmosphere to stellar wind stripping, eventually becoming an airless, lifeless rock. The combination of tidal locking and stellar activity means that many planets in red dwarf habitable zones might be particularly vulnerable to runaway greenhouse effects. If the day side gets hot enough to vaporize water, that water vapor could circulate to the night side and create global greenhouse warming. Once this process begins, it could quickly lead to complete atmospheric collapse, turning a potentially habitable world into a Venus analog in just millions of years. But the Venus trap isn't limited to red dwarf systems. Even planets orbiting sun-like stars face risks that Venus has taught us to recognize. Many exoplanets are likely to lack the protective factors that allowed Earth to avoid Venus's fate. Magnetic field protection, which was crucial for Earth's atmospheric preservation, might be rare among exoplanets. Generating a strong magnetic field requires specific conditions: a molten metallic core, rapid rotation, and the right internal structure. Many exoplanets might lack one or more of these requirements. Super-Earths, planets with masses between Earth and Neptune that appear to be common throughout the galaxy, might be particularly susceptible to Venus-style atmospheric evolution. Their stronger gravity could make it easier to retain thick atmospheres during the early stages of planetary evolution, but it could also make them more likely to experience runaway greenhouse effects if their atmospheric composition becomes unbalanced. Plate tectonics, Earth's crucial climate regulation mechanism, might also be rare among exoplanets. The conditions required for plate tectonics, including the right planetary size, internal heat sources, and surface water content, represent a very specific set of requirements that many planets might not meet. Without plate tectonics to regulate atmospheric composition over geological timescales, exoplanets might be much more vulnerable to atmospheric runaway processes. A planet might maintain habitable conditions for hundreds of millions of years, only to suddenly transition to a Venus-like state when volcanic outgassing or other processes push atmospheric greenhouse gas concentrations beyond a critical threshold. The timing of these transitions adds another layer of complexity to the Venus trap. A planet might be habitable when we first observe it, but undergoing gradual atmospheric evolution that will eventually lead to runaway greenhouse conditions. From our perspective, separated by hundreds of light years and limited to brief observational snapshots, such a planet would appear perfectly habitable, even though its doom is already sealed. This temporal aspect of the Venus trap means that even if we could perfectly characterize exoplanet atmospheres and surface conditions, we might still misidentify worlds that are in the process of climate collapse. Venus itself might have appeared habitable to distant observers for much of its history, even as the processes that would eventually destroy its habitability were already underway. Recent discoveries have provided concrete examples of how the Venus trap might operate in real exoplanet systems. The planet Kepler 452b, often called Earth's cousin due to its similar size and orbit within its star's habitable zone, might actually be a Venus analog rather than an Earth analog. Detailed climate modeling suggests that Kepler 452b could have experienced runaway greenhouse warming despite being in what appears to be a favorable orbital position. The TRAPPIST-1 system, which contains 7 Earth-sized planets and has been hailed as one of the most promising systems for habitability, might also contain multiple Venus analogs. Several of the planets in this system orbit close enough to their host star that they could have experienced water loss and atmospheric evolution similar to Venus, even though they appear to be in potentially habitable orbits. These examples illustrate how the Venus trap could be operating throughout the galaxy, creating a cosmic graveyard of failed Earth analogs. For every genuine Earth-like world capable of supporting life, there might be dozens or hundreds of Venus analogs that appear habitable from a distance, but are actually sterile hellworlds. The implications for astrobiology and the search for extraterrestrial life are sobering. If Venus analogs are indeed much more common than Earth analogs, it suggests that habitable worlds capable of supporting complex life over billions of years might be extraordinarily rare. The conditions required to avoid the Venus trap, including magnetic field protection, plate tectonics, appropriate rotation rates, and stable stellar environments, might represent a very narrow set of circumstances that few planets can maintain. This rarity has implications for the famous Fermi paradox, the question of why we haven't detected any signs of extraterrestrial intelligence despite the vast number of potentially habitable planets in our galaxy. If most apparently habitable worlds are actually Venus analogues, it could help explain why the galaxy seems so quiet. Complex life might require not just habitable conditions, but stable, long-lasting habitable conditions that can persist over the billions of years needed for intelligence to evolve. However, the Venus trap also provides a roadmap for more sophisticated approaches to exoplanet characterization. By understanding the atmospheric and geological processes that led to Venus's demise, astronomers can develop better techniques for distinguishing between genuine Earth analogues and deceptive Venus analogues. Future space telescopes, like the James Webb Space Telescope, and planned missions like the Habitable Worlds Observatory, will have unprecedented capabilities for analyzing exoplanet atmospheres. These instruments will be able to detect specific molecular signatures that could reveal whether a planet has active water cycles, stable climate regulation mechanisms, or signs of runaway greenhouse processes. Key indicators might include the ratios of different atmospheric gases, the presence or absence of water vapor at different atmospheric levels, signs of geological activity through volcanic gases, and evidence of magnetic field protection through aurora-like phenomena. By looking for these signatures, astronomers hope to develop more reliable methods for identifying truly habitable worlds. The search for biosignatures, chemical signs of life in exoplanet atmospheres, also becomes more complex when we consider the Venus trap. Oxygen, often considered a key biosignature, could potentially be produced by non-biological processes in Venus analog atmospheres. Meanwhile, truly habitable worlds might not show obvious biosignatures if life there follows different chemical pathways than Earth life. Understanding the Venus trap forces us to be more cautious and more sophisticated in our approach to exoplanet science. It reminds us that the universe might be full of worlds that failed to achieve or maintain habitability, and that finding genuine havens for life might be more challenging than we initially hoped. Yet this challenge also makes the discovery of truly Earth-like worlds more precious. Every genuine Earth analog we find represents not just a potentially habitable world, but a world that has successfully navigated all the pitfalls that destroyed Venus and countless other planets throughout the galaxy. The Venus trap teaches us that in the cosmic search for habitable worlds, appearances can be profoundly deceiving. A planet that looks like paradise from a distance might actually be hell, while genuine havens for life might be far rarer and more precious than we ever imagined. Venus stands as a warning beacon in our galaxy, reminding us that the path from potentially habitable to actually habitable is narrow, treacherous, and littered with the remains of worlds that almost made it. We know the risks, but now we're going back. After decades of neglect, Venus is having a renaissance. The planet that once captured imaginations as Earth's mysterious twin, only to be dismissed as a hellish dead end, is suddenly the hottest destination in planetary science. A new armada of spacecraft is preparing to pierce Venus's veil of clouds and unlock the secrets of our solar system's greatest climate catastrophe. These missions won't bring Venus back to life, but they might finally answer the questions that have haunted us for decades. Was Venus ever habitable? How did it die? And most importantly, what can it teach us about the fate of worlds throughout the universe? The renewed interest in Venus represents a dramatic shift in scientific priorities. For most of the space age, Mars captured the lion's share of attention and funding. Mars seemed more accessible, more Earth-like, and more likely to harbour signs of past or present life. Venus, by contrast, appeared to be a cautionary tale written in sulfuric acid, interesting but ultimately less relevant to understanding habitability and life. But Venus has been quietly revealing its secrets, and those secrets have profound implications for planetary science, climate change, and astrobiology. The isotopic evidence for massive water loss, the complex atmospheric chemistry, the geological mysteries hidden beneath the clouds, and the climate lessons for Earth have all combined to make Venus one of the most important targets for future exploration. Leading this new wave of Venus exploration is NASA's Da Vinci mission, short for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging. Scheduled for launch in the early 2030s, Da Vinci represents the most ambitious attempt to study Venus's atmosphere since the Soviet Venera missions of the 1970s and 80s. Da Vinci consists of two main components: an orbiter that will study Venus from space, and a probe that will descend through the planet's atmosphere to the surface. The orbiter will map Venus's gravitational field with unprecedented precision, revealing details about the planet's internal structure and geological evolution. It will also study how Venus's atmosphere escapes to space, providing real-time measurements of the processes that have been stripping away the planet's water for billions of years. But the real star of the Da Vinci mission is the atmospheric probe. This sophisticated spacecraft will plunge through Venus's atmosphere, taking measurements and images as it descends toward the surface. The probe is designed to survive the journey from the top of Venus's atmosphere down to the hellish surface, enduring temperatures that rise from -100 degrees Celsius in the upper atmosphere to over 460 degrees Celsius at ground level. As it falls, the Da Vinci probe will analyze the composition of Venus's atmosphere at different altitudes, looking for clues about the planet's history and evolution. Most importantly, it will measure the ratios of noble gases like neon, argon, and xenon. These gases don't participate in chemical reactions, so they preserve pristine records of planetary formation and evolution processes. The noble gas measurements could finally resolve the question of whether Venus ever had oceans. Different formation scenarios predict different noble gas ratios, and by comparing Da Vinci's measurements to theoretical predictions, scientists hope to determine whether Venus started wet and lost its water, or began as a dry world that never had a chance for habitability. Da Vinci will also measure isotope ratios with unprecedented precision, including the deuterium to hydrogen ratio that provides evidence of ancient water loss. These measurements will help quantify exactly how much water Venus has lost over its history and how quickly that loss occurred. Perhaps most intriguingly, the probe will take high-resolution images of Venus's surface during its descent. Venus's thick atmosphere has always made surface imaging extremely difficult, but Da Vinci's cameras are designed to peer through the haze and capture detailed views of the landscape below. These images could reveal geological features that provide clues about Venus's climate history, including possible evidence of ancient rivers, lakes, or coastlines. Working alongside Da Vinci will be NASA's Veritas mission, short for Venus Emissivity, Radioscience, INSAR, Topography, and Spectroscopy. Veritas is an orbiter mission designed to create the most detailed maps ever made of Venus's surface and interior structure. Veritas will use synthetic aperture radar to peer through Venus's clouds and map the planet's surface with resolution better than 30 meters per pixel. This is sharp enough to see features the size of football stadiums across the entire planet. The radar will also be able to determine the composition of surface materials, potentially identifying different types of rocks and minerals that could reveal Venus's geological history. One of Veritas's most important goals is to determine whether Venus is still geologically active today. The mission will look for signs of active volcanism, tectonic movement, and other geological processes that could be shaping the planet's surface. understanding Venus's current geological state is crucial for interpreting its past evolution and for understanding how planets maintain or lose habitability over time. Veritas will also study Venus's gravitational field in exquisite detail, mapping variations that reveal the internal structure of the planet. These measurements could determine whether Venus has a liquid core like Earth, and whether the planet ever had or could still have geological processes similar to plate tectonics. Joining the NASA missions is the European Space Agency's Envision mission, currently planned for launch in the early 2030s. Envision will focus on understanding Venus as a complete planetary system, studying the connections between the planet's interior, surface, and atmosphere. Envision carries a sophisticated suite of instruments designed to answer fundamental questions about Venus's evolution. The spacecraft will use radar to study the planet's surface and subsurface structure, potentially revealing buried geological features that preserve records of ancient climate conditions. One of Envision's most intriguing capabilities is its ability to study the interface between Venus's surface and atmosphere. This boundary region, where the planet's solid surface meets its dense CO2 atmosphere, is where many of the chemical processes that shaped Venus's evolution would have occurred. By studying this interface, Envision hopes to understand how Venus's surface and atmosphere have influenced each other over geological time. Envision will also search for signs of active geological processes, including volcanism and possible tectonic activity. Recent orbital observations have suggested that Venus might be more geologically active than previously thought, and Envision's high-resolution instruments could provide definitive evidence of ongoing planetary processes. Beyond these major missions, several other space agencies are planning their own Venus explorations. The Indian Space Research Organisation, ISRO, is developing the Shukrayaan-1 mission, which will study Venus's atmosphere and surface from orbit. Russia's Roscosmos, building on their historic success with Venera missions, is planning new Venus exploration missions that could include both orbiters and landers. This international focus on Venus represents a recognition that understanding our neighboring planet is crucial for understanding planetary evolution throughout the universe. Venus holds keys to questions that affect not just our solar system, but every planetary system we've discovered around other stars. The timing of these missions is particularly important because they're arriving at a moment when Venus studies are experiencing a revolution in both observational capabilities and theoretical understanding. Advanced computer models can now simulate Venus's climate evolution with unprecedented detail, but these models need data from real measurements to validate their predictions. The new Venus missions will also benefit from decades of technological advancement since the last major Venus exploration efforts. Modern instruments are far more sensitive and capable than their predecessors, able to make measurements that were impossible during earlier missions. Computer processing power allows for much more sophisticated data analysis and real-time decision-making during planetary encounters. Perhaps most importantly, the new missions are designed with specific hypotheses in mind, rather than simply exploring to see what they might find. Scientists now have detailed questions about Venus's evolution, and the missions are equipped with instruments specifically designed to answer those questions. The Da Vinci probe, for example, isn't just measuring atmospheric composition randomly. It's looking for specific isotopic signatures that will reveal whether Venus formed with Earth-like amounts of water, or whether the planet was always dry. The mission is designed to distinguish between competing theories of Venus's origin and evolution. Similarly, Veritas isn't just mapping Venus's surface for the sake of making maps. The mission is looking for specific geological features that would indicate past climate conditions, such as mineral formations that require liquid water or surface patterns that suggest ancient river systems. The data from these missions could fundamentally change our understanding of planetary habitability. If the missions confirm that Venus once had oceans and Earth-like conditions, it would demonstrate that habitable planets can undergo complete climate collapse, with profound implications for evaluating potentially habitable exoplanets. If the missions show that Venus was never habitable, it would help define the narrow range of conditions required for a planet to maintain long-term habitability. Either result would advance our understanding of what makes worlds suitable for life. The missions could also provide crucial data for understanding climate change on Earth. By studying Venus's extreme greenhouse effect in detail, scientists hope to better understand the feedback processes that could affect Earth's climate future. Venus represents the ultimate case study in runaway climate change, and understanding it could improve our ability to predict and prevent dangerous climate tipping points on our own planet. But perhaps the most exciting possibility is that these missions could discover something completely unexpected. Venus has surprised scientists before, and the planet's complex evolution might hold secrets that no current theory predicts. The combination of multiple missions from different space agencies, each with complementary instruments and capabilities, maximizes the chances of discovering something revolutionary about our sister world. The return to Venus also represents a broader shift in planetary science toward understanding worlds as complete systems rather than focusing on individual characteristics. Venus can't be understood by studying just its atmosphere, or just its surface, or just its interior. The planet's evolution involved complex interactions between all of these components over billions of years. The new missions are designed to study these interactions, providing a holistic view of how Venus became the world we see today. This systems approach could reveal fundamental principles of planetary evolution that apply throughout the universe. As these missions prepare for launch, Venus is transforming from a symbol of planetary failure into a laboratory for understanding planetary success and failure. The data they collect won't bring Venus back to life, but they will help us understand how planets live and die, and how rare and precious worlds like Earth really are. The missions to Venus represent more than just scientific exploration. They're an attempt to understand one of the most important cautionary tales in our solar system, and to learn from that tale before it's too late. Venus holds secrets that could help us preserve the habitability of Earth and identify genuine havens for life throughout the cosmos. Venus may be dead, but the data it holds could save other worlds, including ours. Standing at the end of Venus's story, we're left with a tale that's simultaneously ancient and urgent, distant and intimately personal. 4.5 billion years ago, two worlds began their journey through time with nearly identical starting conditions. Both had the right size, the right materials, and the right location to become havens for life. Both received energy from the same young star. Both developed thick atmospheres through the same volcanic processes. Both had the raw materials needed to create oceans, continents, and perhaps even life itself. Yet today, one of these worlds hosts billions of species in a delicate dance of biology and chemistry, while the other has become a monument to planetary death. Venus stands as proof that the universe doesn't owe us habitability, that the conditions for life are far more fragile and temporary than our everyday experience suggests. The Venus story forces us to confront uncomfortable truths about our place in the cosmos. Earth isn't habitable because it's special in some fundamental way. Earth is habitable because it won a series of cosmic lottery drawings that Venus lost. We have a magnetic field because our planet happened to maintain the right rotation rate and internal structure. We have plate tectonics because Earth formed with the right composition and temperature conditions. We avoided runaway greenhouse effects because we ended up at just the right distance from the Sun with just the right atmospheric evolution. Each of these factors was contingent, not inevitable. Change any one of them, and Earth might have followed Venus's path towards sterility. The sobering realization is that Venus's fate was probably more likely than Earth's success. In a universe filled with planets, most worlds that start with seemingly favorable conditions probably end up more like Venus than like Earth. This perspective transforms how we think about life in the universe. The discovery of thousands of exoplanets has revealed that planetary systems are common throughout our galaxy. Rocky planets orbiting in their stars' habitable zones are probably numbered in the billions within our galaxy alone. But Venus teaches us that being in the habitable zone is just the beginning of a long and treacherous journey toward actual habitability. Most of those billions of potentially habitable worlds are probably Venus analogues rather than Earth analogues. They might have started with promise, but crossed climate tipping points, lost their magnetic protection, failed to develop plate tectonics, or succumbed to any number of other planetary disasters that Venus has taught us to recognize. This doesn't mean life is impossible in the universe. It means life is rarer and more precious than we might have hoped. Every genuinely habitable world represents not just a place where life might exist, but a place where countless things went right over billions of years. Earth isn't just a planet with life. Earth is a planet that successfully navigated all the pitfalls that destroy habitability and continues to navigate them every day. Venus also serves as a mirror for understanding Earth's own fragility. The same physical processes that destroyed Venus still operate in Earth's climate system. While we're not in immediate danger of Venus-style runaway greenhouse effects, we're conducting an unprecedented experiment with our planet's atmospheric composition. We're adding greenhouse gases at rates far faster than most natural processes, potentially pushing Earth toward tipping points that could fundamentally alter our world's habitability. Venus reminds us that planets don't gradually transition between climate states. They can undergo rapid, irreversible transformations that completely change their character. Earth has experienced smaller versions of such transitions throughout its history, and understanding Venus helps us recognize the warning signs and potential consequences of pushing our climate system too far. But Venus is also a mystery that continues to surprise us. Despite decades of study, we still don't know for certain whether Venus was ever habitable. We don't know exactly what triggered its climate collapse, or how quickly that collapse occurred. We don't fully understand the complex atmospheric chemistry that maintains Venus's current hellish state. These mysteries matter because they affect how we interpret every potentially habitable world we discover around other stars. If Venus was once Earth-like, it tells us that habitability can be lost completely and permanently. If Venus was never habitable, it helps define the narrow conditions required for worlds to support life. The upcoming missions to Venus represent humanity's attempt to solve these mysteries before they become critically important for our own survival and our search for life elsewhere. Da Vinci, Veritas, Envision, and other missions will provide the data needed to understand Venus's evolution and apply those lessons to Earth and exoplanets. These missions also represent something deeper: humanity's refusal to accept Venus's current state as the final word on our sister planet. We're going back to Venus not to colonize it or terraform it, but to understand it. We're treating Venus as a teacher rather than a failure, recognizing that even in its current hellish state, Venus has crucial lessons to offer. The data these missions collect will help us answer some of the most profound questions in science. How common is habitability in the universe? How stable are the conditions that allow life to flourish? What are the warning signs that a planet is losing its habitability? How can we protect Earth from following Venus's path? But even as we prepare to unlock Venus's secrets, the planet continues to serve its most important function, reminding us of what we could lose. Every breath of Venus's poisonous atmosphere, every degree of its scorching surface temperature, every droplet of its sulfuric acid rain, tells the story of a world that had everything needed for life except the ability to keep it. Venus stands as both warning and inspiration. It warns us that habitability is fragile, temporary, and contingent on factors beyond our direct control. But it also inspires us to understand planetary evolution well enough to recognize and avoid the pitfalls that destroyed our sister world. In the end, Venus's greatest gift to humanity might be the humility to recognize how extraordinary Earth really is. We live on a world that has maintained habitable conditions for over 3 billion years, surviving ice ages, asteroid impacts, massive volcanic eruptions, and countless other challenges that could have triggered Venus-style climate collapse. This recognition should fill us with both gratitude and responsibility. Gratitude for the incredible fortune that allowed Earth to become and remain habitable. Responsibility to understand and protect the delicate systems that maintain our world's habitability. Venus reminds us that we don't get second chances with planetary climate systems. Once a world crosses certain thresholds, once it loses its water to space or its magnetic field to cooling, once it undergoes runaway climate change, the damage is permanent on any timescale relevant to life. Earth is still habitable, but it won't remain so forever. Even without human influence, our planet faces natural challenges that will eventually end its ability to support life. The sun will continue to brighten, eventually pushing Earth beyond the same thresholds that destroyed Venus. Plate tectonics will eventually shut down as Earth's interior cools. Our magnetic field will weaken and potentially disappear. But understanding Venus gives us the knowledge to make Earth's habitability last as long as possible and to recognize truly habitable worlds elsewhere in the universe when we find them. Venus's death illuminates the path toward life, showing us both what to avoid and what to preserve. The story of Venus is ultimately the story of planetary mortality. Worlds, like living things, are born, evolve, and eventually die. Venus died early and violently, its habitability destroyed by runaway climate processes that left no survivors to mourn its passing. Earth is still alive, still habitable, still capable of supporting the incredible diversity of life that makes our world unique in the known universe. But Earth's continued habitability isn't guaranteed. It requires the same delicate balance of factors that Venus lost billions of years ago. Venus teaches us to treasure what we have while we have it, to understand the systems that sustain life, and to recognize that in a universe of dead worlds, every living planet is a miracle worth protecting. Our sister world's greatest legacy isn't its current hellish state, but the lessons it provides for keeping other worlds, including our own, from sharing its fate. Venus failed so that we might learn. Now it's up to us to prove worthy of the lesson.